Hello, welcome to my another presentations. Today I'm going to introduce you the other of my project. It is called the feed-forward neural network on chip design. We totally have 3 people working on this project, and I'm the leader of the team. The other 2 of my teammates are Max and Elena, and this is the final project for one of my master class, the EE523. It's a digital design class in Cal Poly. So before I get into how we design this feed-forward neural network on FPGA on system Verilog, I would like to introduce you a little bit of the background of what a neural network is. So first of all, in my understanding, a neural network is kind of like a black box. And you give it the input and it return you your desired output. It is kind of like a lookup table too. But the difference between neural network and the lookup table is that you could pass in any continuous number into the neural network and it returns you the number, the output back. And the neural network is kind of like closed. It's kind of the mysterious inside of it, because you normally the way you get the neural network is to train it. You give it the input and the output and let it train by itself. In this case, the neural network that we designed and put on the chip is only the feed-forward part, and we do not have the options to train the network. So for user to use it, you have to train your network first, and then put the weights and the bias into the network, into the chip, and then the chip will act like the black box that I just mentioned. So why is it useful? Normally, when we do a neural network in software, if you're using GPU, then of course you have like a very high parallel processing speed. But if you are using the CPU, or normally in software, calculate multiplications and addition, calculate them one by one. And also, there's a lot of power consumptions when you do it on software. And the good thing about doing everything on hardware is that you could have all the multiplications and the additions working together at the same time. In that way, we increase the processing speed, we decrease the power consumptions, and in our case, we also got the accuracy is down to about 0.2%. Neural network is pretty flexible. It has many applications. Yeah, it's like AI is anywhere right now. And here's the architecture of our network. If you look at the left-hand side, the level 0 block diagrams, you could simply just give it a clock, and I'm going to talk about the clock period later, or the clock frequency later. And you give it the neural network input. What you have to give it is, what other 2 terms you have to give it, is the weights and the bias. For those 2, you have to train it somewhere else in the software and then put it into this hardware. But once you train it, it's just stay there. It's the neural network that you can use for a long time unless your system change. And this block is going to return you the output and the output flag, which tells you the output is ready. And on the right-hand side is the more detail of the structures of our neural network. As you can see that we have up to 15 hidden layers, and each hidden layer have 15 neurons, and we have an input layer with 8 neurons and an output layer with 8 neuron. And this graph is also pretty convenient for us to calculate how many bits of the weights and how many bits of the bias we will need to get for the simulation part of this this project. So the graph showing on the left-hand side is the block diagram, and this is the key part. It's like the heart of this project. is the control unit. So as you could probably already tell that this whole block diagram is controlled with the FSM, and except this control unit, I'm going to explain the control unit a little bit later. Except this control unit, we have the bias register and the weight register. In this case, you probably realize that the size of this register are gigantic. They're pretty big, and the reason is because in this project we only want to test out the neural network how it performs in the hardware, but in real life we will not use any register like that big because it's gonna be a hotspot on the chip, and it also wastes a lot of space and memories. In real life, we will use standard protocol like I2C or UART to shift the data in byte by byte. But in this case, just to be convenient, we kind of skip that step and just use a register to store everything. In the control unit, you could get a more detailed view on the right-hand side of the graph over here. So this is the bubble diagram. So as you can see that, let's say if you have you have a neural network of like 4x3. What I mean by that is like you have 4 hidden layers, and each hidden layer have only 3 neurons. You in the flow in the FSM or bubble diagrams, you get into the layer 4, and all the rest of the weights are going to be 0, so you don't really care about that. And after the layer 4, you could directly go to the output. In that case, we do not have to like waste some clock period over here to go over all 15 layers, and we can directly output it. It increase speed, decrease powers. And to simulate this this neural network on system Verilog, we have to compare it to some to some other performance like on MATLAB. In this case, we use MATLAB to simulate the network, to build a neural network, and to train it also. After we train this neural network on MATLAB, we then use we then get the weights and the bias from MATLAB and put it into the simulation file into the system Verilog. And then we do the simulations here. This simulation is a little bit messy, but you could see pretty clearly that after the layer 4, we have the output, which means our neural network in this case only have 4 layers. So after layer 4, we get the output, and this output is corresponding to this one. We compare this output to the ideal output in MATLAB, and we have about 0.2% error. And for this number, I'm going to introduce to you how we represent this number a little bit later. So we get into the power part. In this case, in this project, the power consumption is about 2.1 watt. But this is not the real case, because you can see that we have about 24% of the power went into the I/O pad. But as I mentioned, in the real case, we will input the weights and the bias, just use 1 or 2 pins by shifting the numbers into the register, shifting the weights and the bias like bytes by bytes into the registers. And this I/O pad is not really going to be the case, because I remember it went up to like about 2,000 something percent of the number of I/O pads in the FPGA. That's not going to work exactly the same way when we actually manufacture the chip. So in this case, we have to take out the power consumption on the I/O pad. This 2.1 watt minus 0.5 watt, what you get eventually is 1.6 watt. And as I mentioned earlier, our register is pretty big, and that caused the LUT to be like 500 something. But in real case, this is supposed to be relatively small because we don't have to use that much of the registers to store values. If we use something like UART or I2C standard protocol. And for the critical path, you can see that the critical path delays is about 10.9 or 11 nanosecond. And we have a slack about 0.571. And in this case, for some of the module, I use the rising edge of the clock. And for the other part, I use the falling edge of the clock. Which means for this, and in this critical path, it actually only use half of the clock period. So in this case, I set the clock period to be 24 nanosecond. And ideally, if you look at this is 11 nanosecond. If you multiply this number by 2, ideally, even though I just use 22 nanosecond, it's gonna work. And just to be safe, I increase it up to 24 nanoseconds, and that explains why we have a slack of 0.571. So for this project, there are few difficulties when we debug and when we design it. So the first one is the FSM debugging. At first, our simulations were not even running because it gets stuck somewhere, and the data it comes out are also red everywhere, and we have to debug the signal all the way from the output back to the input. And most of the bugs are like centered around the data, the number modifications, because the modifications that the system modification in system Verilog could only do modification for positive number, and we have to figure out a way to calculate a negative number modifications. And yeah, we debug the FSM together, and it costs us about 10 to 12 hours. So we have to organize the time really wisely. We have to schedule times such that everyone's available at a certain time to work on it together. And for the floating point is the other difficulty that we encounter. Before I introduce this floating point, I would like to mention that in neural network, we normally would not we would like to normalize the input and the outputs for the neural network. What I mean by that is like when you have an input and output, a set of input and output, you would want to rearrange them such that every number for all of those numbers, they are located in a range from 0 to 1. In that case, we need a pretty good way to represent a floating numbers. In our case, we use 4-digit or 4 bit. We put 4 bit to be in front of the decimal point and 12 bit in front after the decimal point. So this is 12 bit, this is 4 bit here. And for each of the number, we represent each of the number with 2 bytes. So this is called fixed point representations. And we also use 1 bit to represent plus or minus. And we have to do the 2's complements to convert number from positive to negative, negative to positive. And yeah, eventually we get the range from negative 7.9 to 7.9. That's how like the smallest numbers that the fixed point representations could represent is negative 0.79. And the resolutions we got it down to 0.0002. Yeah, these calculations, this floating point, fixed point representation kind of like took us some time to figure out, to discuss whether to put 4 bits over here or 5 bits over here, and it also took us some more times to figure out how to multiply the two value. If let's say one of the values is positive and the other is negative, then we have to do 2's complements and have to figure out some way to store the negative sign and assign the negative sign to the final output later on. So yeah, and the other difficulty we encounter is the memory. As I mentioned, that we have 2 really big registers and they took up a lot of LUT, and in the real case, that's not going to happen because we would not use that much of the register. And the last difficulty is to evaluate whether the output from the neural network in system Merlot is good or not. So to do that, we have to compare the numbers to to what we get in the MATLAB. And that is difficult because for all the weights and the bias, as well as the inputs and the outputs, we have to convert it using whatever we define the fixed point representations. So let's say if I give you a 0.912, you have to, like, let's say this 0 will go into here and you're going to have 4 bits of 0 in front of the decimal, and then you have to convert this into here. We do it for every numbers, for every weights, for every bias, for every inputs and the outputs. It is really time consuming, and we work on it together as a group. And here's the end of my presentations. I really like this group, and I appreciate the work of my teammates. And I hope you like this video. If you have any question, please leave a comment, or if you have my email, just email me or message me. Thank you very much.